Okay. Welcome, everybody. Let's start. I will activate the quiz question for you. I have only one question today. Here you see the link. Make that large. Hope you can all see that. No. The last one. So let's have a look. Which statements about basis functions in feature regression are correct? I will afterwards recap what we did last week, briefly redo the derivation of least squares feature regression. And then this should be also clear. The first thing is we introduce basis functions to transform the outputs of linear regression. This is wrong. Let's see. Who had that? Because actually we are transforming the inputs, not the outputs. Remember, we use this matrix A instead of X, the input data, and A was a feature transformation of the inputs. The second answer is correct. So actually polynomial basis functions were introduced, and the other basis functions that we discussed were Gaussian basis functions last week. And number 3 is correct. As mentioned, we transform the inputs into a feature space. And number 4 is also correct. So we discussed with normal linear regression, we have the issue that the number of model parameters has to be the same as the number of input dimensions, +1 for an offset. And that's very limiting. So feature transformation can be used to avoid that. And the last answer is wrong. All right. So number 2 is correct. Number 3 is correct. Number 4 is correct. 2, 3, 4. Today I only prepared one question. We have many bonus points in total. There are no slides, actually. So the same slides like last time, where we discussed probability theory. I will do many things on the blackboard today. Regarding the organization of the course, we are pretty much in line with our agenda here. Today, we discuss probability theory. I will recap basic statistic concept on probability theory, which most of you will have heard anyways in the past 2-3 semesters. But to be sure we are all on the same page, I'll recap these things. And then I will discuss similarity measures of probabilities and define the Bayes rule with you together. And next week, we will introduce a Bayesian model for feature regression. This week, there's no exercise on Friday. Another important thing. Yeah. Okay. I did not share my screen, so that's all fine. We should see the blackboard here. So let's start with what we did last week. Recap linear feature regression. You remember last time we said, let's define a model. We have some y tilde, and this y tilde is given by a matrix A times W. And we said, okay, W is an m-dimensional feature vector because we already used this feature transformation. And the matrix A is of the dimension n times m. Then this works out. We said we would like, our goal is to compute the optimal parameter W, which can be described as the argmin function over all W's. And you remember we dropped the underline because it was anyways the case that all things are vectors now. Yeah? And we said, okay, we would like to minimize the quadratic error of our prediction to our true values. That's what we did. And then we plugged in the model, argmin over W of y minus A times W transpose y minus A times W. That was our goal. So in the end, computing the optimal values, model values, boiled down to, in the end, minimizing this objective via gradient descent. So we said, okay, let's define the objective to be this y minus A W transpose times y minus A W. Then we applied the transpose operator, we did the multiplication. I keep it short now. And in the end, the result was y transpose y minus 2 times y transpose AW plus the quadratic term W transpose AW. And then we said, okay, let's compute the derivative of this objective with respect to our W parameters. This term cancels. This term has W here, which drops out. So we have minus 2 times y transpose A plus W transpose A, because this is the quadratic term, and x squared, derivative of x squared is 2 times x. 2 is missing, yeah? Thank you. Well, noticed. Then we said, okay, we computed the derivative. We set it to 0 because we want to minimize the objective. It should become 0 in the optimal case. For the optimal power meters, our objective here is 0. You also remember that each of these terms here are scalars. Now, this cancels out. I use now here this blackboard and will continue immediately. So Y transpose A is equal to W transpose A transpose A. Remember, then we want to solve it for W. So we applied the transpose operator. So A transpose Y is equal to A transpose A W. And in the end, we can compute an inverse of this diagonal matrix, of the squared matrix, multiply both equations from the left-hand side with it. Then we obtain W. And the result is called pseudo-inverse. So we have A transpose A, the inverse of it, times A transpose times W. So that was the result that we derived last time in a speedy version. But it's just a repetition of what we did. What we could not discuss in sufficient detail is actually the issue we have with this inverse here, because this A transpose times A might be singular, and then you can't compute the inverse. And you might have faced this issue in the exercise as well. So the solution, so the requirement is that the rank of A is equal to the dimension M in our case. So we said rank of A has to be M. Then we can compute the inverse. Now, if we can't do that, I define the solution here. We can add a regularization term with lambda times the identity matrix A transpose Y. And this solution is now called regularized least squares. And this regularization term lambda typically is a very small value. So ideally you start with a very small number like 10 to the power of minus 6 or even smaller. And if that doesn't help, we try to increase this value 10 to the power of minus 4 and so on. Of course, the regularization will at some point dominate the inverse, and the solution will be an average explanation of your data. So the stronger your regularization term is, the less you focus on the real data values. So in the end, this looks like this term here is a matrix where you have these lambda elements in the diagonal. That's it. Gets added to your A transpose times A squared matrix. There are more sophisticated regularization terms using SVD decompositions and so on. This is the most basic principle that you can apply always. All right. And the other thing was that we said A can be also a feature transformation of X, and then we discussed this polynomial basis function and Gaussian basis functions. I have to clean the floor here, otherwise I will fall down at some point. Everything is wet. Do you have any questions to that? Perfect. Okay. Then we will switch topics. I give you a very brief introduction to the basic concept of probability theory. I show you also the part in the script. Everything is in the script as well. And there are more descriptions in the script, more content. Here we only discuss the basics. So probability theory. This is the big topic today. I will introduce basic concept, then similarity measurement, Keil divergence, and that's it. So we start with a concept called probability space. You don't need to actually take notes. You can take notes, but you have it in the script as well. We denote the probability space by the Greek symbol omega. And as an example, omega could be, for instance, heads or tails, H or T, of a coin. Now, if we have such a probability space, we can define events. Events are actually observations. We denote these events, for instance, by A, whatever we use as a letter. And as an example, A could be that we observe twice in a row a coin flip that lands on heads. Now, in this case, the question is, what is the probability space? Omega. If we do 2 experiments in a row, then what is the probability space then? How many options do we have in total? The probability space must cover all potential outcomes of this experiment. 4, exactly. And then you know, all of you know the answer. So it's heads, heads, tail, tail, head, tail, and tail, head. That's it. Events. Now that we have events, let's define random variables. This is the most important thing. Random variables. And we said these random variables actually may be denoted by a capital like letter X. And random variables actually are functions. Functions that map from a probability space into a real value. That's a random variable, nothing else. So it assigns a real value to observations or events. So in mathematical terms, we denote this by a mapping from the probability space to a real value. That's a random variable. As an example, I have here the probability that our random variable takes the value heads given some parameter mu. Mu is already the model parameter here, is given by mu itself for our coin. And if it's a fair coin, then this probability is 0.5. And same for the probability that we observe tails, given this mu, the mean of our coin flip experiment, is given by 1 minus mu. This is for a fair coin also 0.5. Now, if we have these two probabilities, we can define a discrete distribution. And why is that important for us? Well, distributions are our probabilistic models. So there's one thing we might discuss, properties of these distributions. So for discrete distributions, we can define a probability mass function, PMF, where the probability of our random variable x that takes some value may be denoted by the shorthand P of lowercase x. That's how we do it in our reports, our scientific papers. So we are lazy. We don't want to use the correct complete notation. We use this shortcut. So whenever you read that, that's the probability. And here, this P of x has to fulfill two properties. First of all, P of x has to be between 0 and 1. And the sum of all P of x values over all potential discrete variables, in this case, has to sum to 1. So I'm using the sum symbol for discrete values, random variables, or discrete distributions. I'm using the integral for continuous distributions. Now to give you an example of a probabilistic distribution. That's actually the thing that I want to use in the future. A probabilistic distribution is for us the model, the machine learning model. Remember, y is equal to a times w. In this case, we use a probabilistic model. Now for our coin experiment, I can define such a probabilistic model, P of A, given our model parameter mu, with one term for heads, one for tail. We have mu times A is the probability that we observe heads, and the probability that we observe tails is 1 minus mu to the power of 1 minus A. Now, both things, both events that we can observe are now defined in one model. Now, A can be 0 or 1. If A is 0, this turns to 1. And mu is our probability, the average value of our coin flipping experiment. For a fair coin, it's 0.5. For other coins, it's different. This distribution is called Bernoulli distribution. Now let's introduce the most important continuous distribution, the Gaussian distribution. We had it already, but here it perfectly fits now. So for continuous distributions, we define probability density functions. And for the Gaussian, we use this letter n. And in this case, we have the random variable x and the two model parameters mu and sigma, the standard deviation. And you all know the Gaussian distribution has this normalization term, 2 times pi sigma squared power of 1/2 or the square root of it times the exponential of minus 1/2 divided by 2 sigma squared x minus mu squared. This is the Gaussian distribution that you all know. The one-dimensional Gaussian distribution where x is a scalar, mu is a scalar. All fine, all nice. Important properties are, if we look at this distribution here, we draw that for you in a nice way. Then we might have 1 times sigma here. We might have 2 times sigma. And we might have 3 times sigma. And you all know that the standard deviation defines actually the area here of 1 times sigma means that 86%, 68% of all events observed within 1 times sigma. 95% are covered by 2 times sigma. And if you look at 3 times sigma, then you have even 99.7%. So that covers almost everything. And if you think of statistics and you look at tables and you see the mean values plus minus the standard deviation, yeah, then these statistics describe 68% of the events that you would observe. Now there's another interesting continuous distribution. Which I would like to mention, because this distribution is sometimes very useful if you describe your data. Look at this graph here. I will draw something and you tell me it's a probability density function of some random variable x. You tell me which distribution that is. Let me sketch that. Okay, I give you another one. And yet another one. It's always the same distribution, but covers completely different areas of your probability space. Therefore, it's so powerful. This is the beta distribution. And let me put it right. The beta distribution has two parameters. Did I use B or beta? Let me think. I use beta because B is the beta function. Okay. The script, let's follow the notation of the script. So the beta distribution has two parameters, A and B. Actually, we are missing here the variable, the random variable X, and our two model parameters A and B. Now it's a real distribution. And it's given by the beta function, which makes use of the gamma function. You find it in the script. I don't define it here. And is x to the power of a minus 1 times, let me get that one, 1 minus x. You don't need to know that by heart. B minus 1. So this will be never asked in an exam question that I ask you for this equation of the beta distribution. I might ask you, well, if you look at these distributions here, what is the difference between the settings here? And for this symmetric one, A and B are equal. And in this particular case, they are 1/2. In this case, where the dominant mass is on the left-hand side, B is larger compared to A. And in this case, A is larger compared to B. Different values, completely different areas are covered. So that's the lesson we can learn from this very powerful distribution. Now, one more distribution, then we are done. Actually, one that we use the most in this course is a Gaussian distribution, but not for a one-dimensional random variable, for a multi-dimensional random variable. And then this distribution is called the multivariate Gaussian distribution. And I want to define it now. Over here. The multivariate Gaussian distribution. In this case, we are using our vector notation again. We have the random variable x given the mean mu and now a full covariance matrix denoted by sigma. And this is again given by some normalization term where we have 2 pi as in the one-dimensional case to the power of d divided by 2. So it's actually the square root. And d is the dimension of our covariance matrix sigma multiplied by the square root of the determinant of our covariance times the exponential of minus 1/2 x minus mu transpose sigma to the power of -1 times x minus mu. These are all vectors. And what is very nice about this multivariate Gaussian distribution, that this model is very powerful. So here, for completeness, the symbol denotes determinant of sigma. Now, this is a very powerful distribution. So x could be, for instance, a vector of x, y, z coordinates of a drone flying in a room like here. And you have a model of that. So you have a covariance matrix of that. And then you can answer questions like, how likely is it that x takes a certain value given y and z? Or what is the value of x given y and z? You can do that with this simple model here. And we will find out how we do that throughout this course using conditional distributions. But at its heart, at the core, these models are based on the multivariate Gaussian distribution. Then there, let me see if I will show you that example now. I will show you the example now to make that point clear. So have a look at the script. See here, page 9, multivariate Gaussian distribution. You see exactly the same definition that we have on the blackboard. And we have d-dimensional covariance matrices. And here's an example. If you have your multivariate Gaussian distribution is composed out of two random variables. One is denoted by xa, the other one by xb. And here in this example, xb denotes the ball position in a football game and xa the position of the goalkeeper. You might ask now, using the rule of conditional probabilities, what is the most likely goalkeeper position xa given a certain ball position? So depending where the ball is in the game, the goalkeeper might move towards a certain direction. And you can compute that simply using your mathematical model by applying conditional distributions. And for Gaussians, we can do that in closed form. So we can derive these equations. And you could do that even yourself. If you plug in here the vector, the matrix, resolve this equation here, then you only have xa and xb's in the equation. You can solve it for, in this case, xb. And the result looks like that. You will compute a Gaussian distribution again with some mean mu of a given b and sigma of a given b. And in the end, that's the mean of a and the covariance of a corrected by a projection of b into the space of a. So that's the intuition. You see that here. See, mu of a given b is given by mu of a plus some correction. And the correction computes here the difference between xb and your mean. Xb is what you know. The mean is part of your model. And you project it using here this product of the two covariance matrices into the space of A. That's the intuitive explanation. You can do the same for mu of B given A. And you will find similar equations throughout this course, also for Bayesian regression. All right. Next is Keil divergence. Oh, the Bayes rule comes first. Yeah, Bayes rule. This is important. Standard exam question. I ask you to define the Bayes rule. Yeah, using the definition of a joint distribution where P of A and B is given of, let me put it exactly the same like in the script, P of A given B, the conditional, times P of B. Now we assume that our joint distribution is symmetric. So P of B given A is the probability of P of B given A times P of A. Now these two things are equal. Using this definition, with some rearrangement, I can compute now the conditional of P of A given B is given by P of B given A times P of A divided by P of B. Now, this is a very powerful thing because in the end, you are able to use this Bayes rule to reverse the direction of conditional probabilities. So you might ask, how likely is it that I am at a certain location given some sensor value? And then you can reverse that question and say, given a sensor value and a certain position, the prior of that position, how likely is that? So this term is called posterior. That's typically the thing that we want to compute. The thing that we know, the thing that we can measure, is called the likelihood. And we have a prior. The last thing, which is often neglected in machine learning, is the normalization term. The normalization term B of B can be computed using the likelihood times the prior if we compute the marginal of it. So often you find a different definition of the basal. Let me do that quickly. B of B is nothing else than the sum over all A, actually small a of A, B of A equals A, B. That's the marginal of the joint distribution, which in the end is B of B. And the definition of the joint distribution is here. So it's the sum over all A of B of B given A equals A times B of A equals lowercase a. So sometimes you see the marginal of the joint instead of P of B as normalization coefficient. If you're interested in the most likely posterior out of multiple options, so you're interested in the relative distance to these things or relative evaluation, then you can neglect the normalization term. You need the normalization term if you want to compute probabilities, where the sum of all individual events is equal to 1. Now talking about similarities and the distance between distributions, there's a very common measure that is called the Kullback-Leibler divergence. And I would like to talk a little bit about this distance measure between distributions. This distance measure has some very interesting properties. I would like to discuss them with you. So the concepts that we define here and discuss today will be used in the later lectures. So that's why we do it in that way. But it does not replace a proper statistics course where all these things are introduced in depth. So if you want to compute the similarity of two distributions, let me give you an example. We have here X, our random variable. We have some PDFs. Let's assume we have two. Typical example. P of X and Q of X. And you would like to compute the distance between the two, P and F X and Q of X. And for that, we introduce the Keil divergence. So the Kullback-Leibler divergence, it's like the Euclidean distance for probabilities, for distributions. So it's a distance measure. And it exists for continuous distributions, but also for discrete distributions. There are different notations. So let me, KL. Shortcut is KL here, KL distribution. So the KL of P and Q sometimes is denoted by this notation where you have the KL of P and then these two lines here, Q, to denote the distance measure here of these two distributions. And the interesting fact is, if we look at the equation itself, I will do it now for the continuous case. It's minus the integral of P of x times the log Q of x or x normalized by P of x dx. And here you see an interesting thing. So this distance measure is evaluated for all potential events, occurrences of this random variable x. For discrete distributions, this x could be heads and tails. For continuous distributions, we have to compute the integral. And this distance measure is weighted by P of x. Now the Keil divergence is not so magic. So this is very important. So the KL of P and Q is not the same like the KL of Q and P. And the reason is this importance weight after the integral. And we can actually exploit this property, and I will show you how. So the KL of Q and P is given by the integral of P of Q. So here P of Q is the importance weight times the logarithm of P of P divided by P of Q. Actually, I think in the notation of the script, I only use P and Q. Let me think, check that. No, my mistake. Our random variable is denoted by X. Dx. So in this case, the importance weight is Q of X. Now it's correct. It's correct now. Huh? I see the difference. We have two different importance weights. Now, if we look at the effect now, here we have the probability density function over x. In our case, we had our data, P, and I will sketch now a model. This is our model. Q. In this case, we have a moment matching behavior where we try to model with the single Gaussian distribution here a bimodal data distribution. That obviously might look like that. Imagine you have two solutions. One where you avoid an obstacle where you go to the left around it, like here. And the other solution is turn to the right, which is nice. Now, I tell you to use a single Gaussian distribution to model these two things in 2D. Could be 1D, it doesn't matter. Obviously, your single unimodal Gaussian distribution will compute the average. So the result will collide with the pult here. So this is the moment matching behavior. And you observe that if you apply the KL of P and Q. And why? The reason is the importance weight. If you look at the definition, you weight all these similarities. Similarities are computed by the log of Q of x divided by P of x for each individual event. And you weight it by P of x, which means each of these samples here have high weight. Same here. They are very important. Maybe my sketch is not the best. Probably your Q, model Q would cover a larger area, but it would be the average. So if we look at the other definition of the Keil divergence, this definition is called mode seeking. Here you focus on your model itself. So the difference between your model and your data at each event is weighted by the model contribution. So mode seeking KL or behavior looks like that. You again have your PDF over your random variable X. We have our data, which is bimodal. P, and now our model itself will focus on one of the modes. We'll completely neglect the other one. And the reason is that you use the KL of Q and P. Q of x log P of x divided by Q of x. And this is now the importance weight. So you try to fit with your model a large probability mass area here, and you neglect the rest. So even though that you decided to use a single unimodal Gaussian, you could at least explain one of the two solutions here in our navigation problem. And typically in machine learning, reinforcement learning, that's your goal. You might have seen in your data set multiple solutions to solve a problem because you have experts demonstrations. But in the end, what you really want is at least one working solution and not an average over two solutions that will collide with some obstacle. So you see that there is a subtle difference, and you have to know that. Computing the similarities between distributions is the way to go if you have a probabilistic model and you want to explain your data. So we'll always compute the similarity. How well does my model explain my data? Then you compute some derivative with respect to your parameter, apply some updates, reduce the reduce the KL divergence, for instance, yeah. And then it makes a difference based on the definition of which KL distribution you use. KL divergence. Did I forget something? So the mode-seeking KL tries to explain one mode. If you have a Gaussian distribution, a unimodal Gaussian distribution, you would explain one mode. In the moment matching KL, your data defines what is important based on the importance weights for each data sample. Wherever you have a lot of support in your data, your model should match that. Therefore, it's called moment matching. Sometimes you would like to have a symmetric KL divergence measure. Sometimes this happens. So what would you do? Do you have any idea? So we mentioned the KL is not symmetric, but there's a solution to it. We have enough time. Actually, there are many solutions to it. I will show you two. So for a symmetric KL measure, it could be simply the sum of the two. So the KL of P and Q plus the KL of Q and P. And you now know that these two things are not the same. One solution. There might be a second solution where you take the minimum of the two distributions for each individual event. P and Q and KL Q of P and P. Now you have two symmetric variants. All right, I think these are the important concepts that we will discuss and use in the next lectures. If you like would like to read more about the KL divergence or other things, please have a look at the script. For the lecture, that are the concepts that we will need in the future. And that was really a short introduction and more or less in a nutshell, probability theory of what we need in the future.